Hello. Okay, every time you come to view. So it's exactly the same plan as it always is. The only extra thing is that we've got Sarah Lees here as a teaching assistant. So if you've got any questions that are about anything that I'm not talking about, or you've got any questions in the midsection where I'm talking to somebody else, please feel free to gesture Sarah Lees over and talk to him about questions. I've put our usual question up, so tell me which question you'd like me to go through on the board at the beginning of the class. You'll note a conspicuous absence of question number 4, most of which was optional. So if you've got burning questions about question 4, I'd suggest maybe bugging Sarah Lees about those. But if you could give us a vote on what you'd like me to go through at the beginning, that would be great. Once we've done that question, we'll have probably about 20 minutes or so for individual feedback, so for you to work and Sarah Lees and me to circulate. And then we'll come back at the end, maybe for another question as well. So tell me what question you want me to show you. Don't forget, you can vote for more than one, so if you want me to do just anything, just vote for all 5. Only 5, come on. 7. Okay, so we've only got 10 votes, but so far it's looking like people like question number 6. So, right, looks like that's a throw-up between question 1 and question 6. So if you want us to avoid question 1, get on and put your vote against number 6. Want me to do that, then vote for the other option. Okay. It's looking like we want question 1 and question 2, or question 1 in the first part of question 2 on calculating statistics. So let's do that because it will help with the rest of the exercise sheet. And then the interquartile range of the normal distribution is coming up as a close second, so we'll maybe do that at the end if we've got time for 10 minutes at the end. Okay. So, question one. Question one, we needed to find various different quartiles. So we were given a data set which had 25 pieces of information in, and it's on the exercise sheet for you. And we needed to find the quartiles for P is equal to 0.1, 0.25, 0.5, 0.75, and 0.9. So in each of these cases, the first thing I do is I calculate R, which tells me which value from the sample to take. If it's not an integer, I then need to do some linear interpolation. So first of all, let's find our R's. So the formula for R is P times n plus 1. So in the first case, I'm going to need to do 26 times 0.1. So I'm going to get 2.6. And in the second case, I'm going to get 6.5. Okay. So in this first case, when I've got my R is equal to 2.6, I need to do some linear interpolation. So I need to take the second smallest value in the sequence, and then I need to add a little bit on to get myself to the 2.6th entry. So my estimate for the 10th percentile is going to be this value. And what's going on there? So when I've got the brackets on there, that's from the ordered sample. So I need to sort the numbers so that the smallest one's at the beginning and the biggest one's at the end. And then with the brackets, that's the second smallest. It's in the ordered sample. And then I've got 0.6 times the difference between the third and the fourth one to get me to where the position of the 2.6th entry would be. So that's what that is doing. And the value I would get out is 0.475. Okay, so just to show you again how that one works. So in the second one with 6.5, what would I be doing? I've got to start from the 6th smallest, and then I've got to add on 0.5 times the difference between the 6th and the 7th one to get to the midpoint between the 6th and the 7th entry. So. Okay, so I end up with 2.1055. Now you should be able to see the principle now, so hopefully you could finish off the rest yourself. So that's sort of shown us how to use the formula to get our estimates for the quartiles. So I guess we're okay now with question one. So let's do the first part of question two as well, and then we'll leave you some space to work on other questions. So let's have a look. So the first part of question two, we needed to do the 5-number summary. So we need to use what we've learned in question one to find the median, the 25th quartile and the 75th quartile of the sample that we've been given, and we also need to find the minimum and the maximum value, because those are the things that go into the 5-number summary. So what do we need for part I? All right. So I had 20 values in the table. So first of all, let's when they're ordered, I need to pick the smallest one and the biggest one for the minimum and the maximum. And then using that n is equal to 20, I need to estimate these quartiles again. So this one, the minimum from the data, was the first entry in the ordered sample, which was 29.140. And the maximum, so the biggest one, in the ordered sample was 51.261. Okay, and then I'm going to use roughly the same tactic as I did to find the quartiles as before, but I've got a different sample size. So I need to bear in mind that my n is now 20. So if I've got p is equal to 0.25, so I want to find the 25th quartile, I need to calculate what r is, which is going to be a quarter of 20 plus 1. So 5.25. And then I'm going to have to find in the sequence the 5th and the 6th entry in the ordered sample and then interpolate between those two. Okay, so that first one is 37.0325, and you should be able to do the other two as well. So I'm going to leave the other two for you guys to do. And then the next part of this question, which was not into the histogram yet, was to calculate the sample mean and the sample variance. So we'll make some comments on that one at least. So for the sample mean, you just do what you've been doing with means forever and a day. So your sample mean for this particular sample, so it's a little x because it's for this particular sample. I just need to add up all of the 20 values of xi that I've been given and divide by 20 because my sample size is 20. And I get 40.69, etc. And then with the sample variance, and I'm using roughly the formula that I've seen for variance before, but when I'm dividing by n minus 1 rather than by n, because we'll see why that is later on in the course, but it's better to divide by n minus 1 for reasons that will be developed within the next few weeks. So for the sample variance, I'm going to be using this formula. Let me move that up a little bit. So I'm going to have to square each of the values in the sample, so that's xi squared, and then I'm going to have to take off 20 times the mean, and then divide by 19 in this case, so n minus 1 rather than n. And that's going to give me the sample variance, and I need to take the square root to get myself to the sample standard deviation. Okay. Okay, so that's a sketch of the first question you guys asked for. So hopefully that will get you started a little bit with finding quartiles throughout the rest of the exercise sheet and prime number summaries and such like. So what I'm going to do is I'm going to give everybody at least 15 minutes, maybe verging on 20 minutes, to work on any questions that you've not done on the exercise sheet and attract attention if you need for individual feedback. And then we'll come back at the end and do some of question 6, because it looked like you guys wanted to see question 6 as well. Yeah? Good stuff. So it's quite a big exercise sheet, so I don't know which bit of it to display for you guys. So I'm just going to go for probably the second to last page, or most of the second to last page. Sarah Lee's has printouts if you want to see the different sheet.
I have already given out.
Good stuff. bit loath to disturb everybody because everybody seems to be working really, really well and have things to work on. But we've got about 10 minutes to go, so would you like to see question 6 as well? Yeah, we've got some nodding going on. That's great, that's great. Let's have a look at number 6. So let's just have a look at what the question was first. So the first part here said to revise from probability 1, show that the cumulative distribution function of a normal random variable with parameters mu and sigma had this kind of shifted form. And then the second part said show that the quartile function takes a particular form, and in particular find an expression for the interquartile range of the normal distribution, and then look at our data from question 5 and try and decide whether we think, based on an estimate of the interquartile range, if the data was normally distributed, whether we can conclude that the data from question 5 is likely to be normally distributed or not. So that's the objective. So let's have a look at the answer. Okay. Okay, so the first part, all I needed to do was I wanted to recognise that a CDF, what is that function? It's the probability that our random variable with the given distribution takes a value less than the little x that's been specified, so this. Now we've used in probability 1 lots of places that if we manipulate what's on the left hand side of the inequality in the probability like this, we have to do the same to the right hand side and the probability remains the same. I'm going to standardise the random variable on the left hand side, and it means I'm going to have to standardise the constant on the right as well. Okay. Now at this point I can recognise that my what I've done on the left hand side of the inequality is I've made a random variable which is normally distributed with mean 0 and variance 1. So this I can recognise immediately as the CDF of the normal distribution. Because z defined in this way is normal not 1. Okay, so that sort of got us through the first part. So the second one, our goal is the quartile function looks like this. So what exactly is this quartile function? So what I want to be doing is I want it to be a number such that p% of the observations are less than that number. So I can immediately say, well, yeah, it's going to have to be something to do with f, because I want to be able to plug it in the place of x in f and get out a fixed value. So what I want is I want a number, I'm going to maybe call it q, such that when I put it into f, I get out the p value that I want. Okay, so I want q to return a number y, so that when I put it into the CDF I get p out. And because for the normal distribution, f is nice and strictly increasing, I can just define q as the inverse function. So that's not necessarily always strictly true, but because I've got a strictly increasing function f, that's fine. So, what's this? All right. So with that in mind, we're going to have to try and invert the function f that I found in part 1. So what am I going to want to do? I'm going to want to set f of x in part 1 equal to p, and then I want to rearrange it for x. So I want to define set p like this, and then I want to rearrange it for p to get what I need. Okay. So I'm at this point, so I've managed to get my equation in terms of the y that I was putting into the function f, and that this form here is exactly what I was looking for. It's my QP. Okay, so I'm nearly there. I was then asked for an expression about the interquartile range. So what I want for the interquartile range for the normal distribution is the difference between the 75th and the 25th quartile using this estimate. Okay. Okay. So then I've just plugged the 75% into my equation for y. For the 75th one, I'm going to have to do the same for the 25th one, and some things are going to cancel. Okay. So the mu's are going to cancel, and I'm just going to end up with sigma times the inverse of the CDF of the normal 0, 1, and again. Now everything in the parenthesis here I can actually look up in the normal distribution table. So I'm looking for the entry in the normal distribution table with 25% and 75% respectively. And that's going to give me just a constant, and it's exactly the constant that I was given in the question. So 1, 3, 4, 9. So no, this one. Okay. So when it came to estimating what the interquartile range should be with the data in question 5, if the distribution was normal, what we can do is we can put our estimate for the sample variance into this equation as indicated in the question. So looking back at question 5, we had that sigma, had the value 16.54, So if we multiply it by the constant that we found, we've got our estimate for the interquartile range under the normal assumption is going to be S times the constant, 16.54 times 1.349, which is 22.31. But the interquartile range that we found in question 6 is quite, in question 5 is quite different from that. So the values that we found in question 5 indicate an interquartile range of the sample, defined as the difference, as always, between the 25th and the 75th quartile as being 17.5, which is a lot less. So it sort of gives us the idea that when we put on the extra assumption of normality, that the interquartile range that we got out under that assumption is really different than the one that we observed on our sample, which kind of implies that it wasn't a great assumption that we were adding, because it was varying from what we were actually observing inside the sample in question 5. So this would indicate that normal wasn't a great assumption. Okay, and I'm sorry to have gone over by a couple of minutes. I hope you don't have anywhere else you've got to run to.
Yeah.